Okay, so now that I've gone over state spaces and tree search, we're going to do a problem on state spaces. So in this problem, it's called the Towers of Hanoi. You may have seen it before. The game is that we have three pegs, A, B, and C, and we have n disks. In this case, we have 4, but we'll write it as from 1 to n. And the goal of the game is to move all the pegs such that they look the same as they are on A right now, but they're actually on C. Apologies, supposed to be getting smaller and smaller. But the one trick is that you can't have a smaller peg beneath a smaller disk beneath a bigger disk. So for example, if we have one peg here, this is valid, a small disk on top of a big disk. But if I have something like this with the big disk on top and the small on bottom, this is not allowed. So that's how the game is played. So what we're going to do is try to come up with a state representation such that if we pass it to depth first search, breadth first search, any tree search algorithm that we want, that it'd be able to find a path to go from this to this. So let's jump in. I'm going to erase some of this to clean it up. Okay. So the first problem is asking us to propose a state representation for the problem. So in general, I like to approach this by thinking of, if I knew all of this, then for sure I'd be able to do the game. As the agent, I would know that I have enough information. So for this game, I look at this, and in my head, if I know where all the disks are, both where they are, which peg they're on, and what order they're, like what height they are on their peg, then that is actually what the picture is showing. So let me write that out. So for disk 1, I would record the peg that it's on and the position. So for example, in this one, I would have disk 1 would be on peg A, and it would be at the top. So it would be at 1. So that's one example. And then I would do this for all the disks, all the way to disk N, and I would also mark the peg and the position. So this will definitely work, but let's stop and let's think, is there any information that's redundant here? So by redundant, let's just consider disk 1. Okay, so we know what peg it's on and we know what position it's on. Now it seems that knowing the peg is important. If we got rid of that, then it could be on A, B, or C. So I think we need to keep that. Now let's think about the position. So the position is important because that tells you what moves you can and cannot do. For example, if we have the current state is like this, and here's another peg with something smaller. If we know the big disk is at top, we know that this isn't allowed. So we need to be able to, whatever our state is, to be able to know that that's not allowed. Now, let's just say I get rid of the position. So now I only know for all the disks what peg they're on. But since we're not allowed to make illegal moves, I know that all the smaller pegs are above the bigger pegs. So that gives a total ordering. So that means I don't need to know the position anymore. So let me go into this in a little more detail. So let's say I have 3 disks. I have small disk, a medium disk, and a very big disk. And I ask you, what's the valid ordering of them on a peg? Well, there's only one. Biggest, medium, and small. So that's how I can get rid of the position. So now for disks 1 to n, all I need to know is what peg they're on. Moving on to B, what is the size of the state space? So what I can do is, for each disk from 1 to n, I can go, how many values can that take on? So I can be on peg A, B, or C, so that's 3. So for disk 1, I have 3. Then I also have another, for disk 2, it can be on A, B, or C. So that's also another 3. And I go all the way to disk N, and it also can be on either peg A, B, or C. So that's 3. So when I multiply those together, I get 3 to the N. Okay, so now I'll move on to C. So given the state representation in A, what would be the start state? So given what I wrote, it would be something like disk 1 will be on A, and they'll all be on A. So it'll be disk N will also be on A. And from a given state, what actions are legal? So an action is illegal if, what I drew here, you try to move a big disk onto a smaller disk. So what we can do is, for each peg, we can find smallest, well, not smallest, let me erase that. We're going to find the peg on top. Sorry, find the disk. Keep mixing them up. Find top disk on each peg. And then once I know, well, first ask yourself, can you find the top disk on each peg? Well, by what we talked about in A, where there's a total ordering, which is right here, I can always find the top disk. Then, for A, B, and C, I know the top disk and I know what size it is, I can determine whether it's valid. So you can only move top disk to another peg if that disk is smaller, the one that you're moving, compared to the one that you're moving onto for the other peg. Okay, so now what's the goal test? Well, this is very similar to C. So the goal test is if disk 1 is in C, and disk 2 and disk 3 all the way up to disk N. And that completes this part. Okay, so now we're going to do some tree search problems. So above we have a state space graph with a start state right here, and a goal state here, and a bunch of other nodes A, B, C, and D. And they have some edge costs, and also this H, which I'll talk about later. And now for all the algorithms, you'll need to know the states and where the edges go, and only for some of them will you need to know these edge costs, like this 2 or this H right here. So first, we're going to start with depth first search. Okay, so in depth first search, you can view it, if you want to view it from a coding perspective, as, so it's a, so we're doing this. So it's going to be a stack. That's how you maintain what's on your fringe. And by that I mean you push to the front, so you push new nodes to the front of your stack, and you also pop from the front. Okay, so now I'll go through the steps, and this can be similar to how you want to do it, or if you come up with another method that's easier, well, please let us know. So we have the start state S, and that's the only one on our stack at the very beginning. So what I do is I pop it off, and what do I add? I'm going to add SA, adding all of its neighbors, SB, and SD. Notice how I include the full paths, not just the last one. This is important because at the end we want to know not where we ended up, because that's always going to be the goal, if you can get to the goal. We also want to know how we got there, because that's what we're searching for. Okay, so I've pushed these on, and by depth first search, we pop from the front. So notice that I put them on in alphabetical order. So that's how we decided to break ties, so alphabetical order. So the problem will usually tell you how to break ties. Okay, so we're going to pop SA, and we're going to push it on its children onto the front. So SA becomes S to A to C, and it also becomes, well, actually that's it. And then we have, you keep the rest, the previous stuff that was not popped. So we have S to B and S to D. So now I pop them from the front. Now where does SAC go? Well, it can go to two places. It can go SAC D, and it can go SAC G, and then we keep the previous SB and SD. Okay, so now you're looking at this and you see, oh wow, okay, here's G, it's on my stack. Okay, so I'm done. No. So you only are done when you pop. So when you cross it off and you see that the state at the very end is the goal, then you're done. So by depth first search, I crossed off the first one, it's D, so I need to still keep going. So where does this go to? So D only has one neighbor, so S, A, C, D, G, and then I keep the rest. Okay, so now I pop from the front. Oh, I see my goal is right here, so this is actually my solution. Shouldn't have crossed it out. So depth first search, we'll go this windy route, S to A to C to D to G. Okay, so now we're going to do breadth first search. So what can you view it as? We're going to view it as, so it's in code, it would be a queue. So when you got a new path, you would push to the front and you would pop from back. So this might look familiar from 61B, your data structures class. Okay, so as usual, we start off with state S, and it's the only one on there, so we cross it off. Now I'm going to push onto the queue, and I'm going to push in reverse alphabetical order when there's multiple children. So SD, SB, and SA. Okay, so according to breadth first search, I'm going to pop from the back. So I take A, and what does A expand out to? It expands out to C. So then I'm going to get S, apologies, S to A to C. Note that I'm pushing onto the front, and I keep the rest there. Now I pop from the back, and where does SB go to? It only goes one way, one to one child. SB, D, and then I keep the rest. Again, I take from the back, which is SD, and SD also only goes to one place. So S, D, G, S, B, D, and S, A, C. Okay, so note again that G is in my queue, but I'm not done yet. It needs to get to the very front, and I need to pop it. Now, what you could notice is that just because everything always moves to the right, no other path is going to jump in front of this. So SDG will end up being our solution. But for completeness' sake, I'm going to keep going, but just keep this in your mind. When you're running breadth first search and you see the goal, that's going to be the path that you're going to find. So I take from the end and do SAC, and SAC goes to two places, but I go in reverse alphabetical in which I'm pushing, so I'm going to go G, and then S to A to C to D, and then I keep the rest. S, D, G, and S, B, D. Okay, so now I pop from the back, and where does S, B, D go? It only goes to one place. S, B, D, G, S, A, C, G, S, A, C, D, and my last one is S, D, G. Now I'm going to pop that off, and I'm done. I found the goal state. So that's best first search. Okay, so now I'm going to do uniform cost search. So we can view uniform cost search as, in code, it'd be a priority queue. So what do I mean by that? So we push path and the cost onto, and we pop the cheapest path. So that's what we're going to do. Now note that we're actually going to have to take into account these edge costs now. So before we just ignored them, but now we're going to use them. Okay, so I start off with state S, and it has cost 0. So there's only one thing I can do. Take that off. And because I'm going by cost, I don't really need to keep an ordering when I'm writing down. I can just write them down in any order because it's the cost that matters. So I have S to A as a child. And what's the path cost? Well, it's 2. And I also have S to B. And what's the cost? It's 3. And I have S to D, which is a cost of 5. Okay, so now I pop the cheapest one off, which is SA, because it has the lowest value of 2. So now, where does SA go? Well, it goes S to A to C. So I take this cost here, 2, and plus the cost of the new edge, which is right here, which is the 4. So that'll be 6, and then I keep the rest. Okay, so now what's the cheapest? Well, SB, it's 3. So where does SB go? It only goes to SD. Alright, it goes to D. So the new path will be S to B to D, and that'll be, it was 3 plus the new edge, which is 4, so that's 7, and then I keep the rest. Okay, now SD is the cheapest. So I pop that off and I add where it goes. So it only has one child, S to D to G, and that's cost of 5 plus another 5, which is 10. And I keep the rest. Great, now the cheapest is SAC, which is 6. And now I have to add 2, because there are 2 children. So I'm going to add SACD, which is 7. And I'm also going to add SACG, which is 8. And then I keep the rest. So SDG of 10, so I'm running out of room, and SBD, which is 7. Okay, so now what's the cheapest? So I have SB, so I actually have a tie. So SBD and I have SACD. So how do I rate the tie? I go alphabetically. So they're both D, so I need to go back to a previous letter. So I have B versus C. B comes first. So I'm going to take that off. Now where does that go? So SBD only goes to one place. So it's SBDG. And that's going to have a cost of 7 plus another 5 is 12. And then I add all the previous values on. So I have S, A, C, D of 7, S, A, C, G of 8, and S, D, G of 10. Hopefully you guys can see that. Okay, so now what's the cheapest? Well, I have SACD, which is the cheapest, and I'll expand that to SACD can only go to one place. So SACDG, and that's going to have a cost of 7 plus 5 is 12. And then I also am going to add all the previous ones. Now I'm running out of space, so I'm just going to draw arrows. So I take that guy, this one, and this one, and they'll all be here. Now I have 12 versus another, this is cost 12, this is cost 8, this is cost 10. So I'm going to pop the 8 and I see my goal. So I'm done. So the cheapest path is SACG of cost 8. Okay, so now we didn't cover these in lecture. Well, you might have by now. But I'll do greedy search and A-star search. Well, first I'll do greedy search. So greedy search. So greedy search is probably the simplest one. So now we actually need to look at the nodes and these H values. So these H values are given to us and they say, well, this is how far we actually think we are from the goal. So here we have B is H equals 5. So the H equals 5 says, oh, I think that B is the shortest distance to the goal is 5. Now, what is the actual distance? Well, it's going to be 4 plus 5, which is 9. So this H isn't correct, but it can sometimes help us, which we'll show in A-star. And as you learned in lecture, probably by now, these H values, if you constrain them, they can have different properties of optimality when doing your searches. But I won't go into that. So for greedy search, it's pretty simple. You just follow the cheapest route. So, and the cheapest route is only by the H's. So you're only looking at the H's. So I start at S, which they don't tell me what the H is, but it doesn't matter. It's still only 1. So I take that and I add S to A, and I look at the H value, it says 2. I add S to B, which says 5, and I add S to D, which says 1. So I'm only looking at the H values. So I would take the cheapest one off because I'm greedy. So S to D. So where does that go? S to D to G. And they actually don't write H here, but what they meant to write was whenever you're at the goal, H equals 0. So that, and we keep the previous ones. And we pop off the cheapest, and we see our goal is there, so this is the path that we found. So you can see why they call it greedy. What is the actual path cost? So S to D to G is a cost of 10. But by the previous problem, we know that we can actually find a cheaper problem than 10. A cheaper path than 10. So greedy won't always be optimal. Okay, so now we're doing A-star search. So A-star search is going to be very similar to uniform cost search, but we're also going to incorporate these H values. And as I said before, if these H values are chosen correctly, then it can often be a faster search, so it'll require less steps. So how are we going to do this? So for a star, what is it going to look like? So it's going to look exactly like uniform cost search. So we're going to have a priority queue. And what do we put on it? We put on the path, since we need to remember that, and the path cost. So if I just stopped here, this would be uniform cost search, but it's going to be the path cost plus the heuristic, which are the h's. So now let's start running through this. So we're going to start at state S, which is going to be 0 plus, they actually don't tell me the h value, but again, it doesn't matter because it's the only one, so I'm going to choose it. Now I add the children, S to A, and the path cost is 2 and the h value is 2. I'll explain in a little bit why I kept them separate as opposed to writing 4. So S to B is going to be 3 plus 5, and then S to D will be 5 plus 1. Okay, so now we remove the one that's cheapest. So it's going to be the 2 plus 2, which is 4. Now what I add is I add all the children, which there's only one, S to A to C. And here you'll see why I kept them separate. So the path cost is 2, and the new edge is 4, so it's going to be 6. And the heuristic, which I look here, is 2. If you just added them together, then you would be double counting, because the heuristic would stay in there. But we don't want to keep the heuristic from the previous, from A. We only want the heuristic from C and the path cost. And then we write down the rest of what's on our priority queue. Sorry, my 5s look like S's. Okay, so now what's the cheapest one? Well, we have 5 plus 1 is 6. So I removed that. And where does SD go? It only goes to one place. So S to D to G. So its path cost was 5 plus another 5 gives me 10. Plus it's at the goal, so the heuristic is 0. And then I write down my previous members of my queue. Okay, so now what's the cheapest? Well, we have a 6 plus 2 and a 2 plus 5, so those are the same. But we break ties alphabetically, so we remove SB. So where's SB go? It only goes to D. SB, D. So that's going to be 3, which is our previous path cost, plus our new edge, which is 4, so I get 7. Plus what is D? D is H equals 1. And then I keep the previous. Okay, so now the cheapest is, well, we have actually a tie again. SAC and SBD are both 8. I go alphabetically, and I remove the C. So where does SAC go? It goes to 2 places. So SACD, and SACD is path cost is 6 plus 1 is 7, and the heuristic ID is H equals 1, and it also goes to the goal. So SACG is also added. So it's 6 plus 2 is 8, plus it's at the goal, so the heuristic is 0. And then I also add my previous, let's scrunch this, SBD, which is 7 plus 1. And I also have SDG, which is 10 plus 0. Okay, so now what's the cheapest? Well, I have another tie. Yeah. Let's see, yeah, SACD, SACG, SVD, and SDG. Okay, so I have a tie, so I have three-way tie, D, G, and D. Okay, so D is first. If I go back, there's C and there's a B. Okay, so I take SBD, and I take it off. So SBD only goes to one place. Goes to S, to B, to D, to G. And that's going to have a cost of 7 plus 5 for the edge cost. So that'll be 12 plus sum at the goal is 0. And then I keep all the previous ones. So S, A, C, D. S, A, C, G plus 0, and S, D, G, which is 10 plus 0. Okay, so now look at this, and I also have another tie. So I have SACD is 8, and SACG is also 8. So I go alphabetically, and I remove SACD. So SACD only goes to one place, goes to G. So I do S to A to C to D to G. So it's a cost of 7 plus another of 5, which is 12. Plus I'm at the goal, so the heuristic is 0. And then I write down the rest of my priority queue. So now I look at what I have. I have 12, 12, 10, and 8. I pop off the 8 and I see my goal is there. So I found my cheapest path of 8. And that's A-star search. So if we actually compare this with what we did with uniform cost search, I don't think we actually got any savings from running A-star. But that actually depends on H. If your H's are very good, which I won't get into, then you'll do a lot less steps.